So I'm pleased to introduce Dan Murfet, who's talk next, who was a professor at University of Melbourne, originally from kind of very pure math, then kind of decided safety was important, and kind of is now kind of full-time embedded in this field. More recently switched away from Melbourne to lead Timaeus, which is a nonprofit working on signal learning theory. And I think in general, like Dan is trying to bring a level of rigor which I think is not embedded in the overall picture space. I think both for SLT and like you kind of thinking about other parts of the field. We also just hired one of Dan's students, AC. Thank you, Dan. Thanks, Joe.
Small correction there. Okay. So I'm head of research at Timaeus, but Jesse is the executive director. Okay, thanks everyone for coming. Yes, I'm originally from algebraic geometry, so that's where I started life. Amusingly, my academic grandfather was David Mumford. I don't know if any of you know Mumford. If you're in computer vision, you would, yeah. So yeah, it sort of skipped a generation or something, the interest in learning. Okay, so I'm going to say a bit about SLT. SLT is singular learning theory. So I'm going to tell you what that's about, or at least sketch some of the broad ideas and one of the major theorems. But I want to start by, well, first of all, mentioning the founder of the field, so Sumio Watanab, brilliant mathematician, in my opinion, vastly underknown and undervalued. Really very brilliant, very beautiful work. Series of papers going back. I mean, some of the early results was, 2001. So some very important work from 2 decades ago. Ended up in 2 books. They're excellent books, and his art is also excellent. So if you go to his webpage, there's even more. That's quite enjoyable. Okay, so I want to straight up address the question of why should you believe that something, I mean, there was algebraic geometry in the hills there, right? Which is not usually known for being relevant to machine learning, let alone alignment. So let me address straight up what the argument is here for why this is relevant. I'm going to do that by outlining how I think about what alignment is trying to do. We laid this out in more detail in a position paper that you can find on the archive. We here is going to mean some combination of my collaborators at the University of Melbourne, particularly Susan Way, and she's now at Monash. She's a statistician, my PhD students and graduate students, and the folks at Timaeus. Okay, so we're familiar with the idea that capabilities and alignment of modern AI models are specified indirectly by engineering the data distribution, right? A lot of effort is put into preparing the data, shaping the data, so as to indirectly control the behavior of the final trained model. But an important and perhaps underappreciated, although not unappreciated, property of this mode of engineering is that it's underspecified, right? So given that data, there are many different ways of performing the task so as to achieve low loss. Many distinct ways, which has the implication that if there are multiple different ways of achieving low loss, then those different ways might behave differently in situations where you aren't actually evaluating the model, whether by loss or some kind of post-training inspection that's based on input-output behavior. And that's one way of thinking about things like goal misgeneralization. Okay. So I claim, at least from my perspective, that this kind of character of the nature of the systems we're producing is core to a lot of the problems that we worry about in alignment. And so that means that any techniques, theoretical or empirical, that get at understanding those differences, right? The differences within the set of things that you could end up producing by your engineering process. Understanding those differences is broadly useful within alignment. Okay. And that's, of course, what interpretability, for example, is about, right? At least significant degree. And we heard from Roger Gross earlier in the week about exactly this kind of thing, right? The science of generalization, and generalization being to do with what the model is going to do once you take it out of this training paradigm. I claim that SLT is an interesting and sort of deep, at least mathematically, component of addressing these kinds of questions, which historically have been sort of understudied within statistical learning theory for various reasons. Okay, so that's the sort of way I think about the problem. And now I'm going to sort of in the rest of the talk lay out what kind of things it has to say, what the theory, why the theory, how the theory underlies those things that you can say about these questions, and then empirically how you can turn that theory into things you can do in real models. Okay, so an outline. So I'm going to start off by basically jumping straight in the deep end and exhibiting to you how I think about a particular situation and how the background intuitions and modes of thinking from SLT maybe let me think about it differently than you might. You might find that interesting. I'm just going to not really fill in the theoretical content in the first part. Then I'll backfill that in the second part. Then I'll talk about experiments, and finally about some of the work we're now doing, sort of what we refer to as structural inference, like trying to figure out internal structure in models from the point of view of SLT. Okay, I'm actually going to come back to this. Let me just start with some, apologize, that's probably pretty small in this room. So my notation is going to be that Dn is a data set of size n, sampled IID from some distribution. Lnw is going to be the negative log likelihood for that data given some parameter w. And so w is parameterizing some model px given w. And there's some prior distribution phi w. So then the posterior distribution given the data set is some normalizing constant 1 over Zn and times this factor here. Given that posterior distribution, I can ask the question. So now let's turn to this graph on the right. So the x-axis here is parameter space. The y-axis is loss. You can take that to be this empirical loss, the negative log likelihood. And I've identified two regions here in parameter space, curly U and curly V. Here is the population loss. I'll come back to this in a bit, but the surface here is the large n limit of the empirical loss. I've got two local minima, U and V, and I can ask the question, given some data set, what is the probability that if I sample W from the posterior, it's going to lie in, say, curly U? That's just the integral over that region. And so it has this expression. And this lets me define the free energy, which is sort of a central quantity in SLT and in statistical physics, of course. The free energy is defined so that that exponential is that term, that integral there. So the free energy of the region U, given the data set Dn. The data set isn't indicated here, but this is a random variable that depends on Dn. It's negative logarithm of that integral. Okay, so the point of introducing this quantity is to be able to talk about the following kind of question. Is it more likely that my parameter is in U or V? Now, this is all about sort of Bayesian statistics, not about SGD, right? I'm just right now talking about just the posterior distribution. Okay, so if I want to know whether a parameter, yeah, well, by definition, that probability is 1. That's a bit unfortunate. Let's see. Did I do this anywhere else? No. There's a W. That's what it should be. Okay. So W. So what I'm looking at is what is the probability that a parameter given Dn according to the posterior lies in V, and the ratio of that to the probability of U, if you like. Okay. The logarithm, and you can check in your head that that's the difference of these free energies. All right, so if I have a question of the form, which is more likely, that's just a question about whether that ratio is greater or less than 1. That's about whether this quantity is positive or negative. And so it's about these two quantities and their difference. So if I had complete knowledge of the free energy, then I would be able to answer all such questions. And going back to the previous slide, that seems like broadly useful, right? I mean, putting aside the difference between SGD training and the distribution of endpoints there, and what the Bayesian posterior does, But if you were training by sampling from the Bayesian posterior, then knowing the answer to all such questions would go a long way towards helping with a lot of those points. Of course, you don't know that, right? It's a bit like you can solve all thermodynamics if you know exactly how the entropy depends on all the variables. Yeah, that's great, but you don't. But SLT actually is like the state of the art in telling you about this quantity. It's an asymptotic expansion in n, and that's what I'm going to tell you about in a bit. Okay, but first of all, I want to make the claim, I want to explain what this part of the diagram is about. I want to make the claim that as a broad phenomena in Bayesian statistics for wide classes of models, including neural networks, the following kind of thing can happen, where notice that this difference depends on n, and as n changes, conceivably, depending on the form of that function of n, sometimes it could be positive and sometimes it could be negative. If it was sometimes positive and sometimes negative, then over here that would mean sometimes the posterior would be concentrated in U, and sometimes it would be concentrated in V. That could depend on n. All right, so that's one of the interesting phenomena that's, I mean, possible if you're not using SLT to imagine that happening, but it's promoted to like what looks like a pretty pervasive and important phenomena once you understand SLT. Okay, but does this actually happen? Yeah.
Since we're talking about Bayesian stuff here, should we imagine a prior function that's like a quadratic that's over to the left? Is that kind of what's going on here when you say there's a training arrow that's pushing it to the right?
Yeah, thanks. The training arrow is kind of left over from where I got this diagram, so I don't really want to talk about that just yet. But yeah, for example, yeah. The prior, it's true. I'm kind of ignoring. Yeah, you could. This of course depends on the prior.
This is telling me the probability that I end up in such region weight space versus a different region. So like, what's the pragmatic connection to how I translate knowledge of this to like something I'm gonna change about my model or whatever?
Yeah, good question. Let me come back to that later. Please remind me though if I don't. So the question was, so supposing you had complete knowledge of this, how would you actually use this to change? For example, you could use it to select data differently. That would be the predominant way that I would. So I'll actually mention this.
Would I be right in seeing sort of a weak connection to the notion of identifiability in statistics?
Yeah, that's what I'm talking about. I mean, that's what, on the previous slide I was talking about.
In the previous slide, I saw the connection more clearly, but here, now that we're not asking, now that we have posteriors, we wouldn't expect the parameters to concentrate somewhere. There could still be a bit of a distribution.
That's right. So this kind of, what I'm presenting on this slide is relatively trivial in the case where your model is identifiable.
Right.
So this kind of phenomena can't really happen. I mean, it can happen, but it's like actually to do with lower order terms in the free energy, and sort of like, it's a phenomena, but I don't think you really need to take it super seriously. But does this actually happen, say when you're training models with SGD, right? Okay, so I want to tell you quickly about a very concrete setting, and I'm going to zoom through the setting, but I want you to like see how concrete it is or something. So there's a setting in which people have studied in-context learning, where you train transformers to do in-context linear regression. So you take a transformer, the inputs aren't tokens, they're just vectors. So the x's are vectors in R to the D. In the particular experiments we did, that was R to the 8. The y's are just scalars. And the transformer sees in each context a particular linear regression problem. So for a particular task. So this is some Gaussian noise. The different contexts have different tasks. So if you're a transformer and you look at the X token, and you've seen nothing else, it's a bit hard to predict what Y is going to be. Actually, since the mean of the task distribution is 0, you should actually predict 0. So you can actually figure that out and encode that in the weights, and the models do. But as you see more examples of XY pairs related in this way for a fixed T, you can, of course, figure out what the latent regression vector is, and the models do pretty well with this. Okay. So the important thing for me is that you can tune how many tasks you're showing to the transformer over training. Right? So every time you're making a context, you sample a task, and you could choose to sample that task uniformly from some set of M tasks. Each context is a different task, but there's only ever M tasks that the transformer sees. So that's called the task diversity. And if you're doing that, then the Bayes optimal thing to do, now whether or not the transformer can actually encode this in its weights is a different question, but the optimal thing to do would be to compute the Bayesian posterior predictive distribution on the task. Yeah.
So the task that the model has selected, does that impact choosing the X, or is it only the Y condition?
Sorry, it wasn't detailed enough. It's only the Y condition on X. The X is just sampled. They're just random, just Gaussian distribution at the origin.
So here, I'm wondering why we call this posterior predictive distribution. Because usually when people talk about posterior predictive distribution, it refers to a distribution for a random variable, but here the T seems to be the weight.
Yeah, so in this case, the class of models on which I'm forming the posterior distribution is just this set of tasks. Each such task gives me, like, if I conditional on believing this is the task, I would make certain predictions of Y given X.
Yeah, so in that case, why not just posterior distribution, but why adding the posterior predictive?
Well, I have some degree of belief about the tasks, and given that degree of belief, I can predict Y given X. So I'm taking some sum of all the tasks of the prediction of Y given X, weighted for each task on how likely I think that task explains the previously observed XY pairs in the context. Yeah.
Why are you calling this a memorized solution?
Yeah, I mean, anytime these terms memorize is used, it's sort of like a bit unclear what that means. But suppose that you observe the transformer actually, well, in some sense, appearing to predict as though it was doing this. That could mean that in function space, its predictions are very close in some distance, or maybe its losses actually look very close to that predictor. Then in some sense, you would say somewhere in there must be the tasks. Now that may not be true, because maybe there's some other trick for predicting this exact distribution, which, like, by some miracle doesn't actually encode the tasks in any way. And obviously there's some precision, like it's not going to encode those tasks to infinite precision, et cetera, et cetera. But when I say it's a memorizing solution, I'm referring to the fact that it's like not this. Right? So you could just learn to do ridge regression, in which case, like, you don't care what the tasks are. So yeah, it's, I mean, the language that is often used is kind of sort of attributes to the transformer, like, more precision about the knowledge of what it's doing than you actually have. And I'm guilty of that, but that's what
I understand.
Yeah, task specific would be better, but okay. Like, I'm trying to follow the literature and using the language they're using, but I do agree, yes. Is there a question yet?
Why are you calling this posterior? You're not using the prior anyway. So if your T1 to Tm are different set of parameters that we learn. Is that correct?
No. The parameters are in the transformer, and I haven't named them anyway here.
Yeah, but the
The tasks, that's to do with the data distribution. Yeah, so it's nothing to do with, there's no learning going on with the T's. Yeah, I agree, it's a bit confusing. I mean, I've got a model learning something, and here I'm talking about a posterior predictive distribution, but they're like, they're not. Yeah.
Just to confirm, I think you alluded to this earlier, would be like the solution you would want the model to learn is the model sees the XY pairs, the model infers something about T, and then condition on T, it infers something for generating. Okay.
And you might think, and this is sort of my whole point, that, okay, I prepared this data distribution, I fed you heaps of samples from it, like XY pairs conditioned on sampling a task from these M tasks. Like, you should learn to do this because this is the optimal thing to do. Okay, but it's a bit more complicated than that. Ignore this column for a moment. Here's the task diversities, ranging from just one task up to, well, this is just like resampling the task for every context. This is in a low dimensional projection of the training trajectory. So you can take the predictor, you take the transformer, evaluated on some inputs, you get a point in function space, you can do a PCA on that function space. So this is a kind of low-dimensional picture of the training trajectories. Starting up here, it's the same transformer trained on these different data distributions. Okay. These diamonds are these DIMs. Doesn't matter what the acronym stands for. You can go look at the papers. But this is the optimal thing that I was pointing to on the previous slide for a given task diversity. For low task diversities, it just goes to that thing, right? You can see it goes to the diamonds, goes to the diamond, goes to the diamond. Okay, well, now we're starting to do some kind of weird U-turn. That's ridge. Okay. So the models look like, for some period of training, they're like, okay, this seems like I'm doing linear regression. I should be learning ridge. And then they're like, okay, wait a minute. Like there's something about this data distribution that seems like I could do something more. And then they figure it out. Okay. But there's a big cluster of points down there. Not all of them end up at their DIMS point in function space. I mean, notice these aren't parameterized models. These are just points in function space. But the model seems to like get reasonably close to them. Okay, so now let's come over to the, well, first of all, are there any questions about this left hand? Yeah.
What's the relation between the principal components you're plotting and like whether it works ridge or?
A priori, there's nothing, right? These are just, you stack together the input out. So you take a bunch of sampled inputs, which are common to all these tasks, to all these distributions. So the PCA function space is derived from samples from this single task, which is sort of common to all the models. You sample a bunch of those, you evaluate all the models on that at each point in training. That's some big matrix, you do PCA on that matrix. There's nothing about DIMS or ridge in there, but each one of those predictors can do something to the inputs that you chose to define that function space, and so I can plot it. But a priori, PC1 and PC2 here didn't have to have any interesting relationship to those. So it's actually kind of striking that the DIMS predictors, that's not an input, that's like an observation, that this seems to be how the principal components of these trajectories is organized. Okay, over here, low M, intermediate M, high M. Low M, the x-axis is parameter space. Now, of course, the transformer doesn't like literally do ridge, right? Because it's got to invert matrices somehow or whatever. So it's approximating this somehow, and people have studied this, and it's kind of like plausible that something like this is happening. Modulo capacity constraints. And so. Okay, but in parameter space, let's just kind of suppose that you could actually realize those estimators. Here's loss. Now, the DIMS predictor is the optimal solution. That's the lowest loss for this population loss, always. Ridge is worse. I mean, you can actually measure this. I mean, these pictures are summarizing a bunch of data you can find. The ridge predictor is worse. Now, I'm drawing these local minima with different curvatures to indicate different complexities, right? Because as M increases, well, the memorizing solution, which we suppose knows something about these tasks, and there's more tasks, it makes sense it's more complex. In fact, you can use the techniques I'll talk about a bit later to actually estimate the complexity of the transformer parameter and see that this is in fact the case. Ridge is the same, of course, right? Because it's literally the same parameter. Okay, so for low M, training just goes straight to DIMS. That's what we observe over there. For intermediate M, it seems to get sort of close to ridge and then goes back. But for high M, it actually doesn't go to DIMS. Yeah.
And you go out of the ridge minima and into the EMME minima in the middle for the intermediate M.
Here, you mean?
Actually go up.
No, it does not go up. It's just like hard to draw like a three-dimensional picture. Yeah, thank you. Yeah, it doesn't actually go up. Okay, so this is kind of an interesting phenomena. I don't actually know why this happens. But we have a pretty good explanation for this. It's to do with what I showed you on the previous slide and thinking about the probability of various regions, the posterior lying in those regions. Because here we have kind of competition between two solutions where this one is lower loss well, let's focus on this, the case where this kind of retreat from ridge happens. Here we have two solutions, one of which is lower loss but higher complexity, and the other of which is higher loss but lower complexity. So you have this kind of, and in that situation, you can have this kind of phenomena that I described. Okay, so that's kind of, you see here why I drew this with higher curvature than that. Low loss, high complexity, high loss, low complexity. And in that situation, this kind of phenomena can occur. And I'll make this more theoretically precise later. Yeah.
But any of these phenomena could be explained a little bit from a lens of compression or something like this, where maybe as you have a lot of tasks, the most simple way to compress all of the different tasks is by considering the ridge regression solution, whereas memorization starts to become really, really challenging.
Yeah, that's where I'm going. Yeah.
How does, like, there's been a number of different works that look at in context learning versus in weights learning.
Yeah, that's right.
The other and all that. Like, where are you like solving the same problems and the other things they're doing in a different way? Like, how do you situate this?
Yeah, this is a good question. Sort of requires a bit of a detailed answer. So there's indeed some theoretical papers looking at toy models of in weights learning versus in context learning, and like having two different kinds of solutions, which has a bit of a similar flavor where they point out that there's some difference. I mean, that's usually phrased in a very detailed way about SGD trajectories and like optimization. So we're addressing similar sorts of questions about why does this happen, but from a very different perspective, which is not focused on the details of like the loss and the optimization process, but more on the complexity of these solutions and some sort of a like high-level Bayesian principle about how those trade-offs manifest over training. Yeah, this fits into that literature, and I think maybe you should read the paper to see us like explain exactly how it fits in. But yeah, it's part of that literature. Okay, just to put a fine point on this, this is what you asked for in the data distribution. I mean, maybe you collected this data specifically to aim at this thing, but at least for some range of n, that's not what you get. You get this other thing. I think that's a kind of interesting intuition to have about and I showed you a situation where this happens in SGD training, but notice there's a bit of a mismatch, right? Or maybe a big mismatch between this picture, which is about what does the Bayesian posterior do, and the example I gave you, which is about SGD training for a transformer. Now, nobody knows how to close this gap between the Bayesian posterior and SGD training, and I don't know. It's very interesting, and people should work on it. I'm not making a claim that we know exactly how these things are related, but it's, I think, a reasonable kind of starting point theoretically to say, okay, what would the Bayesian posterior do? And then take the attitude that maybe what SGD training does over many training runs is not like completely alien to that, at least locally. And then go out and see if that matches with real phenomena that you see. And again, we actually find that that is the case. Okay, so there's a gap there, that's for sure. But still, if you look at this literature trying to understand in context learning and transience of these generalizing solutions, I mean, there's any kind of theoretical treatment you're going to make has big gaps in it somewhere. So I think this is a worthwhile basic fact to know about complex singular models like neural networks, is that this can happen. It's not rare, it's not weird. That the optimal solution, in the sense where the Bayesian posterior wants to be, need not be the lowest loss solution. This is like a very strange counterintuitive thing, I think, for a lot of people, right? This is normal. I have millions of examples like the previous one. Yeah.
The dim solution is the lowest loss solution.
Right.
But you're saying it's not the Bayesian optimal.
That's right.
Okay. How does that follow from
Well, what is Bayes optimal is not an empirical statement.
Okay.
So I obviously don't know what like the actual posterior for the actual transformer does. That's a very like complicated question. So empirically, the behavior is consistent with that.
Okay.
And the theory suggests that this is kind of pretty reasonable given the values of the loss and the complexity that are involved. Okay. Okay, so I mean, maybe this is, I don't know how significant this point is in the final analysis or whatever, but I think it's one of those things which seems kind of obvious to someone who thinks about SLT a lot, that this might be relevant to these kinds of questions, which maybe isn't, on your mind if you're not engaged with this kind of theory. Given the earlier slide where I suggested that, engineering the data distribution is kind of the way you control behavior, you might want to know how big n star is, right? And before you go stacking a million specifications or a giant constitution on your optimal solution, you might want to consider the fact that increasing the complexity of your optimal solution is actually making this trade-off worse, right? So these are interesting, important dynamics in the optimization landscape. Yeah.
What is there a context you're thinking of where the blue one is desired? Because to me, intuitively, when I look at this, I would expect that generally I'd actually rather do something like ridge regression than try and some random list of t's. Like, I would think that this is kind of the red is kind of more robust to new things happening in the world.
And that's why the Bayesian posterior prefers it.
So,
yes.
Why is there a context where you're thinking of the blue one being the desired one?
Yeah, I had this argument with John Wentworth. He was also of the opinion that I actually think this is safer. Okay, so this is speculative, but I think one case I think about a bit in connection with this is if this optimization problem were parameterizing the policy for an agent. One way we know, at least in kind of a supervised learning setting, one way we know to reduce the complexity of a solution is to do things like error correction. That's sort of a non-trivial fact, but in certain settings, you can prove that if the algorithm that is being parameterized is able to sort of correct for errors that occur during its execution, that's one way of lowering complexity.
Making a bigger basin.
Yeah, making a bigger basin. Okay. And it's kind of conceivable that seizing control of the stuff around you is a way to make your policy robust. So, there's plenty of examples of things. It's similar to that. Robust policies should have lower complexity under this kind of framework. One way so I'm not sure exactly whether I think robust policies in this sense are more or less problematic, but there's some situations in which I can imagine this kind of robustness being a kind of inductive bias for your behavior that isn't necessarily it's an empirical question, partly it's hard for theory to.
I think I missed what's the meaning of complexity here?
I haven't said that. Yeah, that's the theory part. I apologize. I think I have to get to the answer to that. Yeah. Okay, some theory. Yeah, that's what complexity is. Okay, it looks a bit complicated, but well, maybe it doesn't. It's not. Right? Look at, so for a fixed t, so L here is just the population loss. For this empirical loss, the average log likelihood. Q is the true distribution. There's a missing dx here. I'm sorry. So L is the large n limit of the LNW from before. Okay, and this is, I think, a pretty, information theoretically, a very natural object to consider, right? I say to myself, let's look at a local minimum of L. I'm going to look at all the W's which have a loss difference at most T is given, and just take the volume of that set according to the prior. Now the role, obviously this is I've got to go through this pretty quickly. You have to be a bit careful about the prior and so on. So this is actually integrable, but at the end, the prior doesn't matter. Okay, so I'm just going to basically not pay attention. Okay, so that volume depends on W star, this particular local minimum, and the cutoff T. And so I can say, okay, so I took my local minimum, yeah, and that's It doesn't have to be isolated, but let's say it is, because that's what I'm drawing with my hands. Okay, the things with absolutely the same loss as that, it's just 1 point. But as I relax this cutoff, there's some growing region in parameter space that satisfies the cutoff. And I can say at some given t, if I halved the cutoff, that'd be a smaller set. How hard is it to find that set? Logarithm, right? That's the number of bits it takes to locate the parameters with half t that satisfy the half t cutoff within the larger cutoff. Okay. Well, except it doesn't have to be an integer. It's actually a rational number. That's not obvious from that formula. It's kind of a deep fact. So that's called the local learning coefficient of W star. So this volume definition is kind of like information theoretically elegant, not very practical. Are there any questions about this definition? I'll get onto an alternative definition, which is more practical. Yeah.
So that region, is that necessarily topologically connected, or are you also counting other local minima that are nearby?
Oh, yeah, thank you. That's there should also be some kind of ball around W star.
Okay.
That's doesn't actually matter, but I think so. The definition would still work as long as this wasn't going off to infinity. But what I mean by the local learning coefficient is indeed around W star. So given the time, maybe I won't go through the examples, but I'll just say that this is always less than or equal to the number of parameters on 2. D is the dimension of the parameter space. And if the loss near your local minimum is a quadratic form, this quantity doesn't depend on the coefficients of the squares, doesn't depend on the eigenvalues, so it doesn't depend on the curvature, but it does depend on the number of squares. So if you have x squared, but in 3 variables, the local learning coefficient is just a half. You get a factor of a half for each sort of independent variable. So that's the kind of easy case, but then there's more complicated cases. And these more degenerate cases are things that occur in the mean.
It's rational to give
It's always rational. So that's where the deep math comes from. Yeah, so it's always rational by resolution of singularities.
Even if t is irrational.
We take the limit as t goes to 0.
for analytic functions.
And yes. Yeah. Okay. That's right. Everything here should be analytic. But anyway, L should be analytic. You could also think of this as the scaling exponent of the volume as a function of t. A little bit of a lie here because there's an additional kind of log factor, but roughly it's the scaling exponent of the volume near W star. Okay, so a very natural geometric object. Okay, the main theorem of SLT, I wanted to at least put this on the board, but the important thing here is free energy of a region. So take a region in parameter space, it contains one of these local minima. So curly W contains W star, local minima of L. Free energy, which remember was e to the minus free energy, is like the probability of the region, roughly. Okay, so the probability of the region, kind of transformed, is governed by this asymptotic expansion in n. And the highest order terms are something that depends on n with the coefficient, just the loss at W star, and the log n, which has this complexity term in it. This is the main theorem of SLT. There's some conditions. Okay, I really need to just to observe that this question we had before about what the logarithm of the ratio of the probabilities is can be sort of answered with this asymptotic expansion. Right? So it has something to do with the difference in losses and the difference in complexity. So it seems like, therefore, it might be useful to go and see what this complexity is in many cases. So you can attempt to estimate it. Some theorems of Watanabe, this doesn't look like quite the same formula. but this actually so this has some expansion in n, and the so this is an unbiased estimator of the lambda w star. This is lambda hat. So this is more or less what we actually estimate in experiments. This is actually sort of the point of connection to Aditi's talk the other day. Is she was looking at if you perturb the weights by just sampling from a Gaussian near W star, how much does that change the loss? Right? This is kind of a refinement of that, where instead of just sampling from a Gaussian at W star, you're sampling from some local posterior distribution. Local because you're putting, this is just a tempered posterior distribution, but you're putting in this kind of localization factor to try and keep the samples close to W star. Given the time, I'm probably going to have to take questions. Okay, so that's something you can actually compute, provided you can sample from this distribution, which is, of course, very difficult. So what do? You can attempt to use things like SGLD or other approximate gradient-based methods for sampling from posteriors. Well, it's not posterior, but sampling from this distribution over the parameters saved your neural network. That introduces many new hyperparameters for SGLD. It's sort of unclear whether or not it's going to work, but sort of spoiler, it seems to kind of work pretty well. However, we don't really know why. So we're very interested in SGLD and understanding these techniques better. Many experimental caveats, I think I'll skip over them, but the experiments, hopefully you think they're pretty cool, but don't be fooled, like this is like kind of an art. Okay. First observation is, at least for deep linear networks where we know the true learning coefficients. See, I should have said that, like, theoretically computing these learning coefficients is extremely difficult. So we only know the true values in a few cases. And we only, in particular, maybe the only case where we sort of have an interesting class of models where we can dial up the dimension is deep linear networks. And you can do the estimates in those cases using these SGLD techniques and actually get pretty close to true values. Now, deep linear networks are not like the same as the other kinds of deep neural networks you might like to study, but we don't know the theoretical values for those. Okay, so it's not complete garbage. SGLD is not complete garbage for computing this thing. Okay, so then we've gone and looked at a bunch of other settings where you can track this number over training. One of the caveats is that the absolute values of these learning coefficients you shouldn't take seriously, right? It's a 2 million parameter transformer. The learning coefficient's like on the order of a couple of hundred. So it seems like, well, then why should you look at it at all? The point is that if you vary things about the parameter, like you vary it over training, or you vary some other hyperparameter in the truth or whatever, the relative values do seem in practice to give interesting information. Obviously, we care a lot about the absolute value, and we're working on that, but prior to that, we seem to be getting some interesting insight into the development. This is a 2 million parameter language model. There's some sort of learning stages that can be identified here. One of the things I want to point out, it's a bit hard to read, I'm sorry, is that this is the loss over training. This is the learning coefficient. It rises over training. The model's getting more complex. It's learning more stuff. But not always. So this is a model that was trained to do linear regression, as I told you earlier. It's actually that exact setting. You can see that there's some part of training where the complexity actually decreases, and you can look inside the model and see that all sorts of things are happening with layer norm and attention sort of crystallizing. And it's sort of like actually quite interesting as a sort of overall indicator of what's going on inside the model. Okay, but for the purposes of this talk, this is just an example among a few of like going out and seeing what this estimator does in real examples. The next experiments I want to show you actually look at varying a few other things in this estimator. You can look at the parameter over training. You can vary not all the parameters in the transformer, but parameters just in some part of the model, say C. And you can also vary the data distribution you're using to form the loss. Not too far, obviously, because I said local minima, right? So you can't just completely change the data distribution. But you can vary it a little bit and have a look. And there's a more principled treatment of that change coming at the end of the talk. Okay, so what happens when you do that? You can look at attention heads in transformers and see that This is a 2-layer attention-only transformer. These are the layer 1 attention heads and their learning coefficient across training. You can see that sort of things like induction heads seem to be quite low in learning coefficient. Things that are memorizing n-grams, we sort of look at what they do by ablations, seem to be higher in learning coefficient. And there seems to be some relationship between the kind of number of n-grams that are being, I don't think individual attention heads like on their own memorize n-grams. It's not that simple, but according to the probe that we're doing to look at which heads are influential on which n-grams, it seems like the ones that have higher learning coefficient are sort of memorizing more. And you vary the data distribution. So this is the original plot from the previous slide. If you vary the data distribution by changing to code, you can see that this cluster of attention heads behaves very differently to the 2 induction heads in this model, which rise and the other ones fall. So this is leading towards a general picture where you've got this model. It's a very complicated object. You can take a very statistical physics kind of attitude towards it, which is like, I don't know what's going on in there, but what affordances do I have? Like, what can I wiggle on the outside? Like, what external fields can I couple this thing to? We have the data, and you can vary the data distribution. And you can see what happens when you do that. And kind of have the hypothesis that the influence of varying the data distribution might factor through kind of internal structures in the model that are, for example, to do with that structure in the data. Okay, I'm going to skip over this to quickly get to the final part of the talk, but this is basically the point of this slide, is to say we ran this in the Pythia suite up to 7 billion. It seems to work and say kind of interesting things. So this isn't just about toy models. Shame I can't talk about this slide too much, though. Well, it's quite interesting what happens in the Pythia suite across training. Okay, but I want to get to like how we sort of imagine using these techniques to actually say things about internal structure in models. And just to come back to this slide briefly. Right, so ultimately we're interested in, okay, you train a model to low loss, you don't know exactly what's inside it. Those things that are inside it that aren't determined by just having low loss might be significant. How can we look inside to try and figure out what the latent sort of structural factors are that explain those differences? Is sort of a very mathy version of what I was waving my hands earlier and saying. So here's the space of data distributions. So I want to imagine, sort of fix a tokenizer, look at sequences of tokens in that tokenizer. There's a space of distributions over that set of sequences of tokens. And like the pile is such a distribution. So there's the pile, right? This is not the sample space. This space is not sequences. This is like each point here is a distribution over sequences. So there's the pile, there's DM mathematics, there's archive. They assign different probabilities to the same sequences of tokens. If I fix such a distribution, and I fix my model, and I take some samples from that distribution, I get a posterior distribution. And this is a distribution over the parameter space of my fixed model, say a transformer. Again, this is not the parameter space of my transformer. That's not in the picture. This is the space of possible distributions over parameter space. And so each possible posterior is a different point here. And as I wiggle the data distribution, I'm dialing up and down the probabilities of certain sequences. And the model is, that's preferencing certain configurations of the transformer over other ones because they fit differently to that different data. So as I wiggle this point, this thing here is moving around. So I can take the tangent map to that. That's not an object I can put in the computer because there's some infinite dimensional manifold, but the coordinates on that manifold are just expectation values of certain observables. So I take any function of parameters, I can take its expectation value with respect to any posterior distribution I put here. That gives me a real number. And those are some coordinates on this space. And if I just kind of take the tangent map of all that, that defines a map from tangent vectors there, that is change in data distributions to vectors. And that's what we call susceptibilities. So it has a very concrete definition. Given some function phi, and say this is a tangent vector in the space of probability distributions. I take, say, the pile, my training distribution, some other distribution, could be GitHub. I kind of dial down the pile a little bit and dial up GitHub a little bit. Now, GitHub's part of the pile, right? But that doesn't really, still you can dial up the frequency of the probability of certain sequences in GitHub. So that's a little direction in the space of data distributions. I can move in that direction, take samples, compute the expectation of this observable with respect to that posterior distribution, and then take the derivative with respect to that change. Okay, at the end of all that, I've got some number. The numbers, I mean, this is what in physics you call a susceptibility, like magnetic susceptibility, like paramagnetic, diamagnetic. This is the same definition. Okay, so that's some number, and you can go out and you can, you don't want to be like recomputing a posterior distribution for every H or something, so you do something a little smarter than that. You can compute a covariance with respect to the original posterior distribution. What we compute is the susceptibility of a part of the network. So you train your transformer, now you've got a transformer. You pick a part of the transformer, like an attention head, and you pick a direction to vary the data distribution. And you can compute some covariance, and the observable that we choose to compute the covariance for is something that is 0 if you've changed anything outside, I'm out of time, 0 if you change anything outside of the attention head, and otherwise it's just a difference of losses. So it's some kind of measurement of how much changing that parameter has hurt the loss. Okay, so then you can take a small transformer and you can measure these things. Looks like this is for archive, so varying the data distribution from the pile to archive. Over training, you can see different heads in layer 0 and layer 1, different colored curves, have different susceptibility to that change. And you notice that for NIH exporter, I don't know how long you spend staring at the pile, but this is something to do with grants in the National Institute of Health. Not a lot, like very different to archive, right? You see that layer 0, head 0, this blue line is sort of in the middle of the pack here, not really very differentiated. But up there, it's a positive outlier. You might wonder why. Well, you can look at it and see which tokens are contributing to that susceptibility. And you notice that most of the susceptibility for layer 0, head 0 on the archive is coming from curly brackets. So this head is sensitive to curly brackets. If you look at the top contributing tokens here, it's like parts of words. But if you look at the overall scale, this is down in the tail. Like that whole thing there is down in the tail relative to this. So there's lots of tokens that it has some susceptibility for. But it's like got this very strong susceptibility to curly brackets, and like archive contains a lot of curly right brackets. So when you move in the data distribution in that direction, this head's like responding to that external field. Okay, this is just a per token visualization of the susceptibilities. You can see it sort of standing out for these brackets, also left brackets. Okay, but I think I want to wrap up. So SLT, it's a mathematical theory due to Sumio Watanab. There was some gap between this and deep learning, which we've been systematically trying to close over the last few years. Mainly that's consisted of scaling up this estimator and testing it in a bunch of cases to see that it says reasonable things. The thing we're really aiming at with this is to build towards something like a kind of parallel interpretability stack that's based on very different ideas to mechanistic interpretability and ablations and that kind of thing, that's sort of derived from a very statistical physical point of view, a very Bayesian statistics kind of point of view, and assumes for its success some ability to approximately sample from posteriors, not perfectly, but well enough to see something about models, rather than the kind of rather different set of assumptions that would be behind, say, things like SAEs working. And then the aim is, with better understanding of what's going on inside models, to be able to address a range of different problems. Working on more things, but this is the main body of work for now. I'll stop there and take more questions. Another one back there?
Like I'm not super clear on what's the advantage of looking at things like the LSE or susceptibility relative to things that are more grounded in, like, say, evaluations I know about, like these influence function type methods or other things in that.
I think the difference to influence functions is a bit illusory. So, I mean, if you think about how influence functions are motivated, so why are you inverting a Hessian? That's because you could think about that as being like one way of describing what the posterior concentration at the MLE looks like from Bernstein von Mises. It has an inverse of the Fisher information, which is like the Hessian of your loss function. So like the definitions you've seen of influence functions, like if you could perfectly sample from posteriors, like would be actually, the susceptibility I'm defining is actually mathematically very, very close to an influence function. And I'm not spelling that out because it's really like really quite close to an influence function. It's like the influence function isn't sensitive to a part of the model. If I had, if you laid out the mathematical preparation correctly, there would be like one point at which you say, I want to do influence functions, which is a covariance of these things. Or I can do covariance of these things, and one of them is sensitive to a part of the model, and that would be susceptibilities. But like influence functions and susceptibilities, I mean, the way they're implemented, with like inverse Hessians and ECFAC and so on, that's a very different realization of the same underlying mathematical idea. But like the root of that is not very far from what I'm doing here. The big practical difference is that we're using like SGLD and approximate posterior sampling, whereas those kinds of methods are not. But mathematically, there's not so much distance. Evaluations, I'm not sure what you mean by that.
Sorry, I missed the last.
The first part of your question was about like you understand evaluations. I didn't.
Just like if like I can try to estimate the changes of variations in the data I use to train the model.
Oh, I see.
Actual downstream
And just
evaluation.
see what changes. Yeah, that's true, except that doesn't a priori tie those changes in prediction to parts of the model. So we're not just trying to answer the question, what changes, but like, why does it change? And we're interested in varying the data distribution in order to access the answer to that question, because we want to understand what the factors are behind the current performance. And like as a general principle, if you want to understand like why a thing does a thing, you can mess with the thing and see how it changes what it's doing and the pattern of those interventions. And I mean, this is the causal discovery stuff that people are talking about. Yeah.
So I feel like you're making a claim here, which is that the behavior of training algorithms in neural networks has more to do with the exponents of the Taylor expansion of the loss function around a given point than the coefficients of the terms, because this, like, it matters whether it's to the fourth or to the sixth, but it doesn't matter what the coefficient is on the squared term, let alone the fourth term or whatever. And is that a hypothesis that you've tested explicitly, whether those exponents matter more than the coefficients? Because it's surprising to me, but not outrageous to me.
Yeah. I think that's a fair characterization. I'm not sure that it's. So it's obviously difficult. I mean, the population loss, whose geometry controls a lot of this, is possible to access, right? So it's, you don't know like whether or not there are in fact, in some like cases you can derive explicitly like deep linear networks, in fact there are. And so we're in a position of, okay, you have some ways of investigating the loss lengths to get geometry, like looking at approximate Hessians or approximate Hessian rank or the learning coefficient. And it's unclear like, which is a better reflection of the underlying truth in a complex model. So in the theory, the way that the coefficients show up is in the constant order term of the free energy expansion. We've tested in small synthetic examples, you can see that changing the coefficient doesn't change. So like, I'd say in toy examples, the answer is yes. We know the answer is what we say it is. But like for actual like complicated neural networks, it's very hard to know how much, for example, fourth order terms really matter. Sixth order terms or whatever. I think there's one thing I didn't get time to cover, which is there is a setting in which we can answer these questions, which is not neural networks, but where the parameter space parameterizes something called noisy Turing machines. And there you can see a direct connection between all these fine points of the geometry and some internal structure of the machine. It's pretty clear that it's reasonable to expect that complicated internal structure in neural networks plausibly actually corresponds to these kinds of complicated structures in the geometry of the population loss. Under sampling, a lot of that is sort of invisible and comes out only in the statistics of these kinds of estimates.
Out of time. Let's thank Daniel again.
Thank you.
We have a 26-minute break now.
6 seconds.